Okay, so we're still on singular values, and here I want to show you the second part of this definition. I mean, I'm not showing a definition, but I'm showing you that the second part of this definition also makes sense. So the first part that we saw in the previous video was that the eigenvalues of a symmetric matrix, as is the matrix A transpose A, the eigenvalues of such a matrix are real. But here I'm making another claim, and it's that they're not only real, but they're non-negative. Okay? And so this time we're going to show that we have non-negativity of these eigenvalues. So how do we do that? So claim, if I have a matrix A in Mn, then the eigenvalues of A transpose A are real and non-negative. Okay, so this takes us a little further than the previous claim that I showed in the previous video. So in the previous video, what I showed you is that if you have a real symmetric matrix, all its eigenvalues are real. Here, I'm adding more specificity to the matrix. I'm not talking about any real symmetric matrix. I'm talking about a real symmetric matrix that is made by taking the transpose times the matrix. Okay, so this property that I'm giving you here is not a property of all real symmetric matrices. It's a property of real symmetric matrices that are created by taking A transpose times A. Okay, bear this in mind, this is important. So the claim is, as announced, that if I have a matrix of this shape, A transpose A, the eigenvalues are real and non-negative, sorry. So the fact that they are real, we just showed, because we know that A transpose A is a symmetric matrix, and we're assuming that the matrix is real, so we have a real symmetric matrix, so its eigenvalues are real. Now let us show that these eigenvalues are non-negative, and you'll see it's a very, very simple proof. So again, we start with eigenvalues. So let us consider an eigenpair, so an eigenvalue eigenvector pair of A transpose A. And to simplify our life, we're just going to assume that we choose the eigenvector V in such a way that its norm equals 1. And we're allowed to do that. I'll remind you that when you have an eigenvector, any eigenvector that is parallel to that eigenvector is also an eigenvector. Okay, so I am allowed, and it's often very useful actually to do so, to choose an eigenvector that has certain properties. And here, the property that I like is that its norm is equal to 1. Okay, so we take an eigenvalue eigenvector pair of A transpose A. We assume that the eigenvector has norm 1. And now one remark is that norms, they are functions from whatever vector space you're working in into the non-negative real numbers. Okay, so when I consider the norm of AV, the vector AV, and the norm of the vector AV squared, they're both non-negative quantities. Okay, so let me just write this. The norm of AV squared is a non-negative quantity. That is completely correct. But recall that for any vector x, the norm of x squared is equal to the dot product of x with itself. Okay, that's a property of dot products and norms that we saw in the review of linear algebra at the beginning of the course. And this is a very important property. So norm of AV squared is equal to AV dot AV. I'm simply using this equality that I just wrote. And from the consideration we had in the previous claim, when I'm taking the dot product of a vector and another vector, it is equivalent to taking the product of the first vector in row form and the second vector in column form. Okay, so this is what I've written here. So AV.AV is actually the same thing as AV transpose times AV. And now let me develop AV transpose. AV transpose is V transpose A transpose. So when I'm looking at this product, this is V transpose A transpose AV. But now let me group things. So this is V transpose times A transpose AV. Okay, but A transpose AV is the matrix that I started out with, and we chose V to be an eigenpair of A transpose A. So A transpose AV is equal to lambda V. Okay, when I say that lambda V is an eigenpair of A transpose A, that's what I mean. Okay, so that means that this A transpose AV here is actually lambda V, which I write. Lambda is a scalar, I can move it around, and so I end up with lambda times V transpose V, which in turn is nothing but lambda V dot V, which is lambda V squared. Okay, norm of V squared. But I've chosen I've chosen V to have a norm of 1. So that V squared here is equal to 1. And so what I get is that lambda, which equals this, is non-negative. Okay, so that was an easy claim to prove. And as you can see, these are simple manipulations of matrices. Okay, so now we can really dig into the meat of the SVD, and this is not an easy theorem, and I'm not going to prove it. Let me mention this, but this is not an easy theorem to sort of apprehend. So I'm going to spend a little time explaining this to you. So the singular value theorem, a singular value decomposition theorem, is stated the following, can be stated the following way. So let me take a non-square matrix, not necessarily, when I say non-square, it can of course be squared, but it doesn't have to be, okay? So let me take a rectangular matrix of size Mn, and let me suppose it has eigenvalues sigma 1 to sigma r, strictly positive. Okay, so positive eigenvalues, singular values, sigma 1 to sigma r. And then it also has sigma r plus 1 to sigma n, singular values that are 0. And before we proceed any further, let me point out that one important thing here is that when I'm listing these singular values, I'm listing them potentially repeated. Okay, so if, for instance, sigma 1 equals sigma 2 equals sigma 3, so that means one of those singular values has one of the corresponding eigenvalues has algebraic multiplicity higher than 1, then I would list them several times. Okay, I wouldn't write lambda equals 1 has algebraic multiplicity 3, for example, and therefore sigma 1 equals 1 is repeated 3 times. I would simply write sigma 1 equals sigma 2 equals sigma 3 equals 1. Okay, so that means that I have n singular values, but some of them might be equal. Okay, so but what we do is we've seen that from the previous claim that all singular values are non-negative. And what we say here in this theorem is that the ones that are strictly positive, sorry, strictly is the French version of saying positive, but the ones that are positive, I label them up to R, okay? And then the other ones are the ones that are 0. Then what happens is that I can find an orthogonal matrix U in M, okay? So a square n by m matrix U, a square n by n matrix V, and also orthogonal, and what is called a block matrix, and let me explain that later, and a block matrix, capital sigma, and that one is non-square, it's in Mn, and it takes the following form. It has a D on the top left part, and that matrix is a diagonal matrix with the singular values on the main diagonal. Okay, so that matrix is a square R by R matrix with the singular values sigma 1, sigma 2, sigma R on the main diagonal, and everything, of course, being 0. Okay, this is what D looks like. And the rest of the matrix, capital sigma, is equal to 0. Okay, it's full of zeros. And okay, so these three matrices allow us to write A in the following form, which is U times the matrix sigma times the transpose of the matrix V. Okay. Now, let me first come back to the idea about what is a block matrix, okay, before we go any further. So a block matrix, as the name implies, is a matrix which has blocks. And if you want to think about it, so what we have here is a matrix that has that we can cut into pieces, blocks. So that first block here on the top left is a square matrix with R rows and R columns. This and the other blocks are just blocks of 0. Okay, and it's very convenient. I mean, we could write it as the entire matrix, just the matrix with these few diagonal entries non-zero and the others equal to 0. But it's actually very, very convenient to think of it this way. I mean, it's a matrix that is composed of 4 matrices, one which is this diagonal matrix D, and the other 3 that are 0 matrices. And I've indicated, for once here, I've indicated the size of the 0 matrices. Okay, so the one here, for example, is a matrix that has R rows and n minus R columns of the zeros. Okay, so that's why I have these indices here for 0, because here the size is important. Okay, so this is a decomposition theorem. It tells us that for any matrix of size Mn with singular values ordered that way, I can find a matrix, I can find 3 matrices that have the announced shape and that allow me to write A as this factorization. It's another factorization of the matrix A. It allows me to write A in a different form. Okay. And this is very, very important. I mean, it has really nice applications, which we are going to spend some time on, okay? But this is the important part. Now, when we've done this, there are some names that are important to remember. So a factorization, like the one we just did, so A equals U sigma V transpose, is called a singular value decomposition of the matrix A. And the columns in the matrix U and the matrix V that appear in this singular value decomposition, we call them the left and right singular vectors of A. Okay, not eigenvectors, singular vectors of A. But they are linked, okay? So, but you will see that in a moment. And what this operation does is it decomposes. So I'll remind you, this is something I haven't sort of done a lot of reminder about, but that you have seen in first year, that matrices encode linear functions in Rn or in Rm to Rn, etc. Okay, so they are linear transformations. And the transformations that we can encode with matrices, there's several types, but the matrices U and V transpose here, they're orthogonal matrices. And if you remember, orthogonal matrices, one of the things we were discussing before is the fact that they have the property that so for example, if I compute Ux for any x with an orthogonal matrix, I get x. Okay, remember we said this meant that you encoded an isometry, okay, something that does not change for distances. And the type of isometries that are encoded by the matrices U and V that we have here are either rotations or reflections. And you can think, I mean, if you think about it, so suppose I'm working in 2D. If I have a reflection, what this means is that I can have a reflection, for example, could be I'm moving this point here. Okay, this is something like this. And here, if I'm reflecting about the y-axis, I'm not changing the length of the vector. And in the same way, if I'm rotating, so suppose, so for rotations, it's better if I show a vector, and suppose I rotate up to here, well, the vector does not change length, it simply changes orientation. So what the matrices U and V transpose do is that they rotate or they reflect vectors. And sigma, on the other hand, what it does is it scales things. Okay, so when you multiply a vector on the by a matrix that has entries only on the main diagonal, what you're doing is you're changing the order in which, I mean, you're changing the length of the components of the vectors of the vector along its direction. Okay. And so that's a scaling. And so what's happening when you do a singular value decomposition is that you write the linear transformation that is encoded by the matrix A in this very simple form, which is first I rotate or I reflect, then I dilate or I shrink, and then I rotate or I reflect again. Okay, so this is what geometrically the transformation is doing. Now, there's another form that is going to be very useful for us in one application that I'll show you very soon, and it's the outer product form of the SVD. So I'm not going to explain why we call it the outer product. It has to do with some geometric considerations, but this is the way it's called. So the outer product form states the following. So suppose I have a matrix A in Mn, and it has singular values, sigma 1 to sigma r, that are positive, and sigma r plus 1 to sigma n equal to 0. And I look at the left and right singular values of A corresponding to the singular values, and I wrote corresponding to these singular values. I mean to say corresponding to the singular values with that are positive. Okay, look at this. You can see that I'm going all the way to UR and VR, and these correspond to this sigma r that is positive here. Okay, so I only keep the singular vectors that correspond to positive singular values. Okay, so when I have this, then I can write the matrix A. This is somewhat magical, and you will see we'll use this in an application soon. I can write the matrix A the following way. So it's sigma 1, so first singular value, times u1, first left singular vector, times v1 transpose, so first right singular vector transpose. One remark. So we have plus, okay, so let me finish. Plus, and so on and so forth. You continue, you sum all of them all the way to sigma r, u r, v r transpose. Okay. The remark I wanted to make, so sigma are numbers, so it doesn't matter, but let's look at the sizes of things here. So I've been stressing for some time that if I look at u dot v, I can think of it this way, and let me write it sort of visually. So u dot v is the row vector times the column vector. And when you take this as a product, you get, this is an 1 by n, and this is an n by 1. So your result is 1 by 1. So it's a scalar. Okay, that's how we got that u dot v is equal to u transpose v. Now, what happens if we do as is prescribed in this outer product form? So here we're taking u v transpose. So writing this in vector form, we have a column vector times a row vector. And you can guess what's going to happen, which we can figure out right away by writing the dimensions. So this is n by 1, and this is 1 by n. So that means my result is n by n. Oops, yes, it appears. Okay, so this operation here is, and of course I should point out that the vectors are not n by n. Okay, so maybe let me stress this. U, if you remember, U is the matrix U. Okay, let's go back to the theorem so you see it. The matrix U here is in MM, and the matrix V is in MN. Okay, so when I'm looking at things here, U is N times N, and V, did I say M or N? Never get it right. U is M by N, and V is N times N. Okay, so vectors U are M by 1, and vectors VI are 1 by N. So that means that the product UV is M by N. Okay, as is the matrix A. So this is very, very nice because it tells me that I can recompose my matrix A by considering only the information carried by the vectors, the left and right singular vectors, corresponding to the singular values that are non-zero. Okay, so this is, I mean, if you think about it, this is very cool. I don't need to know the entire matrices U, sigma, and V. I mean, it's good that I know them, but I can recompose the matrix A by just knowing the components of the decomposition that correspond to the non-zero singular values. Okay, and as I said, I'll show you an example about using this, and you'll see, I think it's quite a cool example, and you'll see this. Okay, so before I get into examples per se, I'll spend a little time explaining how you would compute the singular value decomposition. And this is, I mean, we're going to do a few examples by hand, and I've planned to do that in a further subsequent video. But before we do this, I want to explain the mechanics of the computation. Okay. So the first thing to know is that there are going to be two cases. If your matrix A transpose A has all its eigenvalues distinct, okay, then it's going to be quite easy. If some of the eigenvalues are repeated, eigenvalues and as a consequence the singular values, but if some of those are repeated, then it's a little bit more complicated. Typically, examples that you'll get in the assignments will be examples that only involve the good case. But be aware that there are cases where it's a bit more difficult. Okay, and we might see them, but if we see them, it would be low-dimensional examples because it gets messy. Okay, so in the case where the eigenvalues are distinct, then there is this other theorem that I'm going to show you again because I think it's a simple proof, but again illustrative. So the theorem states that if I have a symmetric matrix A, and that I have two eigenpairs, lambda 1 u1 and lambda 2 u2, with lambdas distinct, okay? If the eigenvalues are distinct, then the eigenvectors that are associated to these eigenvalues lambda 1 and lambda 2 are orthogonal. Okay, u1 dot u2 is equal to 0. So let's prove this. It's quite simple. It's a single page proof. That's the type of proof that I like. Okay, suppose I have a symmetric matrix. I have two eigenpairs, lambda 1 u1, lambda 2 u2, as announced in the theorem. And I'm assuming that lambda 1 is distinct from lambda 2. And of course, these are eigenpairs, so I should also stress that u1 is non-zero and u2 is non-zero. Okay. I repeat it all the time because it's important. Okay, so let me consider lambda 1 times the dot product of, this should be, I don't know why, all of a sudden they became V's. These should be the same letters. I will fix the sides. So let's call them U's, or let's call them V's. It's probably easier if I do V's. So this is V1 and V2 here. Okay, so what's lambda 1 times the dot product of V1 and V2? Well, as usual, we can move things around. So this is lambda 1 V1 dot V2. And lambda 1 V1, because this is an eigenpair, this means this is AV1 dot V2. We use the same trick as we've been using, multiplying or dot multiplying, dot producting two vectors is the same as multiplying the one on the left transpose by the one on the right. So this is AV1 transpose times V2. But now I perform the computation. AV1 transpose is V1 transpose times A transpose. Okay. So once this is done, well, what do I realize? This is A transpose V2. But A is a symmetric matrix. So A transpose is equal to A. and therefore A transpose V2 is equal to A V2, and A V2, because V2 lambda 2 is an eigenpair, A V2 equals lambda 2 V2. Okay, so this means that I have lambda 2 times V1 transpose times V2, which again is simply V1 dot V2. So what I get is that lambda 1 V1 dot V2 is equal to lambda 2 V1 dot V2. So I can subtract that guy from this one, and I get lambda 1 minus lambda 2 V1 dot V2 equals 0. But I've assumed that the lambdas are not equal. Therefore, their difference cannot be 0. Okay? So the only thing that can be 0 in this product here is the dot product. And therefore, V1 dot V2 equals 0, which means that they're orthogonal. Okay? Okay, so how do we use this to compute the singular value decomposition? And I'll stress again that this is in the case of distinct eigenvalues. Okay, so if all the eigenvalues are distinct, we can use this theorem, and we will be using it soon. So the procedure for computing the SVD in this case is the following. So you're given a matrix A. First thing you do is you compute A transpose times A. That's an n by n square symmetric matrix. You compute the eigenvalues, lambda 1 to lambda n, of this square symmetric matrix. You order them as lambda 1 to lambda n, and that last, so remember, I'm working under the assumption of distinct eigenvalues. That means that all of those little signs, they're strict inequalities, because I'm assuming no eigenvalue equals another eigenvalue. The last one could be 0. That's possible. Okay, lambda n could be 0, but that's the only one that could be 0, because I know that I'm assuming that they're not equal, and I know they're non-negative. Okay. I compute my singular values by simply taking the square root of the eigenvalues. Okay. And then my matrix D in the diagonal block in the matrix sigma, well, it's either an n by n matrix if the last singular value is positive, or it's an n minus 1 times n minus 1 matrix if the last singular value is 0. Okay, so most of the entries in D are going to be there. Okay, where there's not a lot of eigenvalues and singular values that can be 0. At most, there's 1, because we're assuming this different eigenvalue thing. Now, since the eigenvalues are distinct, I can use this theorem that we just showed, okay, which tells me that the eigenvectors of the matrix A transpose A, they form an orthogonal set. Okay, so we didn't stress this, but here, this theorem says that if I have two distinct eigenvalues, then the associated eigenvectors are orthogonal. So all my eigenvalues are distinct. So that means all my eigenvectors are orthogonal one to another. Okay, so that's why we get an orthogonal set. Okay. Because every single eigenvalue taken with another eigenvalue leads to two eigenvectors that are orthogonal. Okay. So I'll compute these eigenvectors now. So I know that they're going to form an orthogonal set. I compute the eigenvectors, and this is very important. I need to compute them in the same order as we've ordered the eigenvalues and therefore the singular values. Okay. Now, I want to create an orthogonal matrix, and I'll remind you that the columns of an orthogonal matrix form an orthonormal set. Orthonormal, not orthogonal. So I have an orthogonal set. I will need to make it into an orthonormal set. So what I simply do is I normalize the eigenvectors that I find, and so I just if a vi is not equal to 1, then I take a new vi equal to vi over norm of vi. Okay, this is what normalizing is. I mean, by now you should know, but repeat it, doesn't hurt. So, and these vectors I put in the matrix V. Okay. Once I have this, I have my matrix V. Remember that what comes up in the decomposition is V transpose. But here I'm making the matrix V. And then to compute the UIs now, all I need to do is for each UI, for each I compute UI as 1 over sigma I times AVI. Okay, and of course this is not going to work if the sigma i's are equal to 0. So we'll do something a little different. Perhaps I'll show you in an example. Okay. And then again, you want an orthogonal matrix, therefore orthonormal columns, and therefore every time you compute one of your UIs, you verify that they indeed have norm 1, and if not, you normalize them. And there it is. You have your singular value decomposition. As you can guess, this is going to be computationally a little annoying. It can take some time to compute this, even for a low dimensional problem. And as you can guess, again, sort of pattern I have been following in this course is I'm also going to show you how to do it numerically using R, and you'll see that it's frustratingly fast to do this computation compared to when you do it by hand. But this is the mechanics. Now, to be complete, let me show you what happens when you don't have all the eigenvalues being distinct, so all the singular values being distinct. So let's compute the singular value. Well, I mean, let me explain how you would compute the singular value decomposition when some of the eigenvalues are equal, so repeated. The beginning starts the same way as in the case where it's distinct, because anyway, you don't know until you've done the computation of the eigenvalues that you have potentially repeated eigenvalues. So you compute your matrix A transpose A, you compute the eigenvalues lambda 1 to lambda n of this matrix, and you order them by decreasing values. Here, now, the inequalities are not strict because I'm allowing some of those eigenvalues to be equal. Compute the singular values by taking the square root of the eigenvalues. And remember that we define the index R as being the one where singular values, and therefore eigenvalues as well, but where singular values switch from being positive to being equal to 0. Now, I'm going to get a bunch of eigenvalues. Some of those eigenvalues are going to be distinct. When I have distinct eigenvalues, I'm fine. Okay, I proceed as before. But when I have an eigenvalue with multiplicity larger than 1, I need to ensure that the eigenvectors that I get are linearly independent and orthogonal. So these are two important words that we need to ensure, and we know how to do this. I mean, so some of it you don't really know yet, but it is easy to do this, but it's costly in terms of time, of course. So let me explain this. So when you have an eigenvalue with multiplicity larger than 1, it can happen, and it's not always true, so this is complicated, that things are more complicated than a sort of general case of a multiplicity equal to 1. So first of all, I'll remind you what we call the multiplicity, and it is the algebraic multiplicity. If you take a more advanced course, and perhaps some of you have seen this, but it's sort of unequal in terms of coverage, there are two properties of eigenvalues. One of them is multiplicities. So one of them is what's called the algebraic multiplicity of an eigenvalue, and that is what is the degree that it comes with in the polynomial. You remember when you're computing eigenvalues, you compute the characteristic polynomial. You have this p of lambda that is a polynomial with the same degree as the order of your matrix. So if I have an n by n matrix, my p of lambda is a polynomial of degree n, and I find the eigenvalues as the roots of this polynomial. So if in this polynomial, for example, I have a term like lambda minus 2 squared, I know that lambda equals 2 is going to be an eigenvalue, a root of the characteristic polynomial. But this root will come twice, okay? Because in this polynomial of degree n, I can once say lambda equals 2 and another time say lambda equals 2. Okay, so lambda has, and that's called the algebraic multiplicity of lambda. Now, there's another thing called the geometric multiplicity of lambda that I'm not going to go into. But so to explain the philosophy, the geometric multiplicity of the eigenvalue is linked to the dimension of the subspace that is spanned by the eigenvectors associated to lambda. And so there are eigenvalues that are called defective when things don't work well. But we know how to deal with it. This is not something that you will see in this course. Okay, I'll give you some hints as to how we resolve this problem, but this is not the main topic here. Those of you who have sort of had your first year course that emphasized diagonalization of matrices might have seen this. It sort of depends. The idea is when you want to diagonalize a matrix, it's not always possible to do so. But so not all square matrices are diagonalizable. But we can find something that is called the Jordan normal form, which is another decomposition of matrices. And that Jordan normal form allows us to have something that is almost diagonalizable. Okay? It gives us a form of the matrix where essentially things are diagonal modulo the fact that some things are not, okay? I don't want to get into the precise details, but that's the idea, okay? So just be aware that when the multiplicity is larger than 1 for an eigenvalue, it becomes a bit complicated. So how do we deal with that? There will be times when you pull out an eigenvalue, it's got multiplicity 2, for instance, and you can find 2 linearly independent eigenvectors associated to it. If that's the case, for example, your eigenvalue has multiplicity 2, you find 2 linearly independent eigenvectors, then you can just proceed to the next step. Otherwise, you need to use this definition here, and these are called generalized eigenvectors. Okay, so we call generalized eigenvector of rank M of a matrix in Mn if it is an eigenvector. It's a vector associated to this equation for M here, but it is not solution to any equation with M smaller than M. Okay, you see this index, this power here. If I have, so it's rank M, if this is true, but it is false for any number less than n. Okay, any power of a to the minus a minus lambda I to powers less than n. In practice, how do we find generalized eigenvectors? So assume I have an algebraic, an eigenvalue with algebraic multiplicity equal to k, and let me point out, this is sort of general. There are cases which don't work, you have to be careful and so on. So that's why, again, in practice, I'm going to provide you with examples which have eigenvalues all distinct, because this gets complicated. Probably I might throw in one or two examples that don't, but in general, this is what happens. So you start by finding out a classic eigenvector. So you just compute it the way you would compute any other eigenvector. That will give you one eigenvector. And now you're going to find eigenvectors of the different ranks. So the first one you'll get by solving this equation here. Taking the first one that I found, I solve for V2, a minus lambda I times V2 equals V1. And I continue. To find V3, I would solve a minus lambda I times V3 equals V2. Okay, continue all the way to a minus lambda I times Vk equals Vk minus 1. And what I get out of doing this is a set of eigenvectors, a set of vectors. Okay, so one is an eigenvector, the other are generalized eigenvectors, and this set is linearly independent. So it's a little bit more complicated than this even. Let me just point out, you might not need to go all the way to here, because it is possible that, for instance, if I'm computing this guy here, I might find two linearly independent solutions V2 that satisfy this. Okay, so once you have enough, you can stop. That's essentially the way you can do. Okay, but let's say that every time you get out a single vector, then at the end, what you have is a linearly independent set. You have your linearly independent eigenvectors corresponding to lambda, whether it is because things worked out quite well, as I was pointing out here, okay, or it is because you've applied this procedure, but you've got a linearly independent set. Well, now you need to make it orthogonal. So you apply Gram-Schmidt to this set to make it an orthogonal set. And now also you, when you have that, you can go back to the procedure we had before. Okay, which means that the next step will be to make it to make sure that these eigenvectors slash generalized eigenvectors also are orthonormal. So we can go back to step 6, which was ensure that all the eigenvectors are unit. Okay, so you can guess that once you run into this type of problem, the computations are a bit longer than they are in the nice organized case where everything is distinct. Okay, so let me now go through I'll introduce two applications of a singular value decomposition. There are plethora of applications of the SVD. SVDs have super important applications both in the theoretical side of things and in the practical side of things. So I'm going to start, I might throw in some more examples depending on how I'm doing for time with respect to other lectures and so on. But for now, let me talk about two examples. The first one I can cover in this lecture, in this video, and the second one I will make a separate video about. The first case that I want to come back to is that the SVD is going to allow us to get unique solutions to least squares problems in all cases, unique solutions. Okay, so they're going to be unique, not quite in the same way as the unique solutions we get when the columns of A are linearly independent, but they are going to provide more guarantee of uniqueness. Okay. And the other example is an example that deals with image compression. That's a practical example of application of the SVD. So let me start with the problem of existence of unique solutions to the linear least square problems. So I'll jump in right away and then I'll explain things. And next time, probably next lecture, but next video, I'll have examples of computing the SVD and examples of using this. Okay. So let me suppose that I have a matrix A in Mn. I take a vector X in Rn and a vector B in Rm. So this is a linear least squares problem. So the least squares problem Ax equals B that we saw earlier, that we saw in least squares problems. It has a unique least squares solution X tilde of minimal length. So that's closest to the origin. I'll explain more in detail when we go into the example. Okay. And that solution is given by X tilde equals to A plus B, where A plus is what we call the pseudo inverse of A. And I'm going to explain in a second, and you'll see how this ties in with the SVD. Okay, so this is essentially the same theorem as we saw before, except that if you recall, when we were looking at the least squares, the unique solution of least squares, we obtain it with A transpose A inverse A transpose B, but that's in the nice case where we can invert A transpose A. Here, I'm not making any claim about invertibility of A transpose A. So we'll need to compute this pseudo inverse, but once we have this pseudo inverse, we can actually find the solution. So what's a pseudo inverse? So suppose I have an SVD for my matrix. So I start out, I have a matrix in Mn, and I compute an SVD, and just in passing. So in the SVD, the sigma has a prescribed shape. And I mean, it has a prescribed and unique shape because it always comes up in the same order. Okay, I order my singular values from the largest to the smallest, and so in the matrix sigma, they are ordered from the largest to the smallest, and that's always going to be the case. The matrices U and V, on the other hand, they are not unique. So that's why I say, suppose you have an SVD, not the SVD. So suppose you have an SVD for your matrix A. D in the matrix sigma is the matrix that contains, I should have the diag of sigma 1 to sigma L. Okay, so it's the diagonal matrix with sigma 1 to sigma R. Then we call pseudo inverse, or it's also called the Moore-Penrose inverse of A. It's that matrix A plus, so it's in NM. So recall, A is in Mn, A plus is in Nm. So the order changes. And it's given by A plus equals V sigma plus U transpose, where sigma plus is equal to the same matrix as before, except that we have inverted the matrix D. And I'll remind you, this is something you should know from first year, but if you don't, it's worth remembering that if I have a matrix D that is a diagonal matrix from sigma 1 to sigma r, and all those values are not 0, okay, then D inverse is simply the diagonal matrix with 1 over sigma 1 down to 1 over sigma r. Okay, so that inverse is very easy to compute. It's simply 1 over the diagonal entries. So the pseudo-inverse is this new matrix, A plus. So once you've computed your SVD, you can compute your pseudo-inverse and get the solution to this problem this way. Okay. As I said, we'll see examples of this. And let me just introduce the other example that I want to look at soon, which is image compression. And as you can guess, we're going to look at this in R, in a Jupyter notebook, rather than here. But let me introduce the problem. So if you think of an image is a matrix. Okay, so the simplest way to think of images is as levels of gray. So for instance, the simplest one is 8-bit encoding. 8-bit means there's 2 to the 8 minus 1, 255 colors, color levels. So from typically 0 is black to 1 is white, and you normalize that. So 0 is black, 255 is white, but you normalize between 0 and 1 often. And what I'm going to show you in the following example, I should point out this is an example I found in a book. I'll give you the reference. This is a book that I'm using from time to time. So what we are going to do is we are going to take the singular value decomposition of the image. I say A, but I'm thinking about my matrix, okay? So my image is a matrix, it has pixels, and in every pixel is simply the value of the gray level there. And I'm going to take this image, apply the SVD to it, and what's going to happen is that, and this is a property of SVDs in general, and it's somewhat magical. You will see it's actually quite cool. The small singular values, they are going to carry information about the regions in the matrix. And it shouldn't be really the regions, it's difficult to explain. They convey about information about where things don't change much. So if you think about, for example, you look at my background there, here, oh my gosh, it's difficult. Here, it's quite uniform in the back. It's a wall with uniform colors. This has little variation. So if you think about it, it's the same color used everywhere. So in my matrix, if you think of this image at one instant in time as a matrix, in the matrix, there's not a lot of variation above my head. So this is going to be carried in terms of information by the singular values that are close to 0. And the associated singular vectors u and v are going to contain this information as well. On the other hand, when there's a lot of detail, this is going to be carried by the singular values with higher values, so the larger singular values. And so what we are going to do is use a sort of partial form of the outer product form of the result. So for a k, so remember that R is the number of non-zero singular values. So for some value k less than or equal to R, I'm just going to define the, we could call it the partial outer product form. It's simply the matrix AK, the image in this case, that I get by, oops, this should be capital T here. It's the image AK that I get by considering the k largest singular values and the corresponding singular vectors. Okay, so for example, if I take k equals 1, I'm only considering this singular value. If I take k equals r, I have the entire outer product form. Okay. And that's what we are going to use to play with images.